Hi, stats class. This is the rest of the lesson 1 guided notes. I am on the bottom of page 5, so you should have done this part, example 4, with me in class today. So now we're just going to finish out the notes in this video. So we talked about stem plots, we've talked about dot plots. One of the other common ways you're going to see graphs or quantitative graphs created is using a histogram. A histogram is a graph that shows an interval as a bar. So it's kind of like a bar graph, but it's not a bar graph. So the heights of the bar are going to correspond with the frequency, the count, or the relative frequency, the percentage of values that fall in that interval. So if I was recording, let's say, I don't even know, heights, then I could have all the people who are 4 feet tall to 5 feet tall, and that bar would correspond with how many of you or the percentage of the class that are in that particular height interval. Likewise, I could do the same thing for 5 foot to 6 foot and 6 foot to 7 foot, and you could just see the general pattern, which is the whole point of this, those different 4 qualities about our class data. When we do this, we're going to choose equal width intervals that span the data. Sometimes it's told to you, sometimes you could pick your own, but 5 is usually a good minimum amount. Any less than that, you're not going to see a whole lot of trends in your data. You also, unless it's a huge data set, probably don't want more than, 10. So we're going to do this for the age of our oldest parent data. And I think I'm going to choose 6 for my number of intervals. That means the number of bars I'm going to use. Now, I might end up finding out like, ooh, that was a crappy choice. Maybe I shouldn't have used 6, but we're going to use 6. So the first thing I'm going to do is make a table that shows the frequency, the counts. I'm also going to talk about the relative frequency, the percentage of my total group that are in each interval. And then I'll talk about that in a second. So I'm going to go to page 6. There's space for example 5 to create this histogram. So first thing I got to do is actually create the table, this distribution. So I'm going to label one part my interval, and the other part's going to be the frequency. So I'm just going to make a little table. Now, the youngest parent was 37. So I'm just going to put 37. And I know the oldest parent was 60. So I need to essentially take that spread of my data and chop it into 6 equal parts. So I'm just going to do 60 minus 37 to find out how spread out it is, which is 23. And I'm going to chop that into 6 parts by dividing by 6. Now I'm going to get a decimal, 3.8. Always round up for that. Even if you get a whole number, you should round up just to make sure you have all available space you need to see your data. So since I got 3.8, I'm going to round up to 4, which means I'm going to have this first interval be all the parents who are 37 years old up to less than 41. The rule is you round up. So any 41-year-old parent would go into the next interval. And this really makes a lot more sense if you're talking heights. Like if these were centimeters tall, 37 to 41 centimeters, you could be just barely less than 41 centimeters. It doesn't really make sense with something discrete like age that we're recording here, but we're just going to keep using this process. So I'm going to keep adding 4. So if you are less than 45, you're going to be in this interval. Once you hit 45, you're in the third group. Less than 49, and I'm going to continue doing this until I have all of my age groups represented. And again, I am just adding that width of 4. And I got that width by taking oldest person, youngest parent, and I chopped it into 6. This number was arbitrary. This is just the number of bars that I would like to have in our histogram. So what was I doing? Adding 4. And then you can see this last one, 57 up through being less than 61 years old. There are 1, 2, 3, 4, 5, 6 intervals like I planned. Now I just need to find the frequency. So I'm going to go back to that sorted data set that we were using yesterday. And I'm just going to count how many were 37 to 41. So I can see 4 parents were in that age grouping. When I look at 40, ooh, I lied. 41 is the roundup rule. I can read. It's not 41. So 37, 38, 41 were the youngest people, so there are only 2 people that are 37 to essentially 40 years old. So now I want the 41-year-olds up to essentially the 44-year-olds. So when I count that, assuming I count correctly this time, I think I see 6. So now I'm looking for 45 up to 48. Sorry, here's an announcement.
Good afternoon, Redbird. Thank you for another awesome day. It is now passing at the end of 6th hour.
I have no idea what they're doing on these announcements. I'm sorry for the distraction. I'm just going to keep counting as we go. I think that's 12. It's 2 and 2. So assuming I counted correctly, excuse me, I'm just figuring out how many people were in each of those groups. I'm going to double check that. I'm going to add up 2 plus 6 plus 10 plus 12 plus 2 plus 2, and it gives me 34, which is the number of people who answered this survey. So I know I at least represented everybody. So I'm just going to note the sum, that's sigma, capital Greek symbol, the sum of my frequencies, and I'm using the letter F for frequency, is 34. So we can do frequencies. It is also sometimes done to, instead of relating how many people, to instead do the percentage of people. Let me try that again. So that's called relative frequency. So it's not just saying, oh, 6 of you were in this group. It's saying, well, what percentage of those who responded have parents from 41 to 44 years old? So you're putting it in context of the whole group. That's why it's called relative frequency. And you do that by just saying, well, if I know 34 is the whole group, how many is 2 out of those 34? So in math terms, that means 2 divided by 34. I'm getting 0.059-ish, so about 6%. So I'm just going to put 0.06. Quick side note, it doesn't matter how you round, which is really hard for some students, especially those of you who are going to be in AP Calculus. The AP Calc test is super rigorous on you always have to round to 3 decimal places. And I mentioned in the other video, AP Statistics is not an arithmetic test, it's a communication test. So they don't care what you round to. Ideally, they would just want to see, oh, they got that answer by taking 2 divided by 34. Cool. They'd rather see what you did and what you do with the information rather than what number you actually ended up with. So I'm going to take those 6 people out of our group of 34, which is around 18%. I'm going to take 10 people out of our group of 34 people who responded. It's about 29%. Same thing for 12 out of 34. And the 2s out of 34. Oh wait, I already did that. And if you sum all of these up, if you sum 6%, 18%, 29, all that, you're going to get 100%. 100% of those of you who responded are in one of these categories. So this is, again, just the chart kind of showing how our class data is separated out. But that's not a histogram. That's just the table. Now we actually have to draw some axes. So I'm going to draw a horizontal and a vertical axis so we can have the height of these bars. The name of our quantitative variable will go under the horizontal axis. So we're going to put it in context of the fact that these are ages of our oldest parents. And then the vertical axis is going to be labeled. Now you can choose, sometimes I'll tell you which one I want to do, but you can do a frequency histogram or a relative frequency histogram. It just changes what you put on that left-hand side. I'm going to try again. Those are not at a right angle. Okay, so again, at the bottom, I'm going to put the age of our oldest parent. And these are recorded in years. The vertical axis, I'm going to do a frequency histogram this time, so I'm going to ignore those percentages we just figured out. I'm going to put in counts. So the answer I got when I just counted those numbers. So it goes all the way up to 12, and they're all even numbers, so that's kind of helpful. 2, 4, 6, 8, 10, 12. The increments you use are kind of irrelevant as long as they are equally spaced and labeled. So technically, I'll point out 0 is here. It is the origin back in your algebra days. But I don't want to start the age. I mean, clearly none of you have parents that are close to 0 years old. The closest was 37. So I'm going to do an axis break. This is the way in math that you kind of cheat, doing things to scale and say, that's 0, but just kind of jump over until something interesting. So that something interesting is the 37 years old. So I'm going to have 37 here. And then I have 4 years later is the start of the next group. 4 years later is the start of the next group. Until I get all of them represented. So we've got our axes labeled. We have equally spaced tick marks. And now we're just going to draw the intervals. We're going to make the bars so that they have no gaps, because a gap is saying that there was nobody in this group, and we never said that there was nobody in a group. So I don't want to have gaps in the bars. So I'm going to have my first bar have a frequency of 2. So attempt to make it look like that. My second group is supposed to have a height of 6. Missed. You don't have to be this persnickety about making it perfect. It's just nice when I have the technology that I can. Also, my hands are shaking because it's really cold in my classroom right now, so it's a little difficult to make straight lines. Oops. Seriously, I can't draw a straight enough line for it to notice that I'm drawing a rectangle. Okay, I give up. It's going to be shaky. So it starts out pretty and then it gets really ugly. Which is honestly kind of an interesting shape to this distribution. It has this nice, slow build up and then suddenly just drops off. I also want to point out how we read this. If I'm wondering, well, I have a 45-year-old parent. Is my 45-year-old parent here or is my 45-year-old parent here? Remember, you essentially round up. If you fall on the interval, you round up and you're part of this next group. So they are not in this group. So that's just the general rule for what you do with histograms. You round up. So once we have another data display, we can answer the question about the characteristics that are evident from this distribution, from this histogram. So we can tell the center, the shape, the spread, and any unusual features. So I'm going to start with the center. I'm looking for essentially the balance point, and I would say it's probably, I don't know, somewhere around here-ish. Again, if you say it's about this age, then you're kind of hedging your bets at the fact that you don't mean it's precisely this. You didn't calculate this. You'd say, it's about 48. So I'm going to put the typical age. Whoa. So it's about 48 years old. And I get, if you disagree with me about what number you think is the center, that's okay as long as it's a reasonable number that you're picking. Like, don't pick 42 or 53. That isn't the center. So the typical age, the center of our distribution, is about 48 years old. So that's the center. I'm going to talk about the shape of it, which is kind of hard to do. But again, remember, you're looking at the general shape. If you zoom out, in general, it's kind of sort of symmetric. It's not great, but I wouldn't say there's a long enough tail really in either direction to call it skewed left or right. So this is weird. I will tell you that on the AP test, they will always have very clear, like, this is clearly symmetric. This is clearly skewed right. It won't be this weird, we have based off of real life data, which is why this one's kind of hard to do. So the histogram is approximately symmetric. And then we want to talk about the variability. So what I want to point out right now, let's pretend that you're not looking at the data set, because I doubt you pulled up the data set when I was filling this out. So you actually don't know, let's pretend you forgot the other video, who was the youngest and who was the oldest. For all you know, there was a 37-year-old parent and a 60-year-old parent. That's actually what there was. That's coincidence. But it's also possible that the youngest parent was 40. I could have had two 40-year-old parents and it would look exactly the same. Likewise, I could have had two 57-year-old parents and this graph looks the same, because remember, as soon as you hit 57, you're represented in this bar of the histogram. When you're 40, you have not escaped this bar of the histogram. So if you are just looking at a histogram, like sometimes I'm going to make you do, you don't get to say, oh, well, the ages go from 37 to 60. Yes, they do for this data set, but don't assume that. So it could be anywhere from the youngest parent being 37 to 40 all the way up to the oldest parent being 57 to 60. You don't know for sure if you don't have the data sitting in front of you. That's one of the problems with histograms. You miss actual data values, so you just kind of look for general trends rather than specifics. So I'm going to put, so with the youngest parent, being anywhere from 37 to 40 years old. We'll eventually get into talking about the range of the data set, and we'll have to be careful here saying what the range would be, because technically you cannot calculate a precise range given only a histogram. And then lastly, anything unusual. We don't really have, I mean, it's kind of an unusual shape, but really when we talk about unusual values, we look for outliers and we look for big gaps, and we don't really have that. So I'm just going to say there are no gaps or outliers. So even though there aren't any of these things, you need to specifically say that you checked for them. You got to check all four of those things. So hold on a second. Can I come back? Okay. Sorry, Ms. Lashke wanted to talk to me. So I'm going to finish these up, and then I'm going to pause the video and put another video for example 6. So compare the stem and leaf plot. Compared to the stem and leaf plot, what does the histogram lack? Well, it's kind of what I was just saying. It lacks exact values. When you look at the stem and leaf plot, you know for sure exactly what ages were where. You still get the same general shape idea, but this one you don't really get to know who was what age. So it lacks individual data values, which sometimes are really nice to know. However, there might be some times that you would actually still prefer to do a histogram instead of a stem and leaf plot. And the reason for that is if there is a lot of data, you're not going to want to just keep putting more and more and more and more leaves everywhere. It's nicer sometimes if you have a big data set to just say, well, let's just chunk them into these groups and then look for the general pattern, instead of listing them all out. Like, if you think about it, if all of you had answered this survey, we would have had to be putting in 63 numbers instead of 35. Can you imagine 63 numbers on that stem and leaf plot, or even just trying to count up all of them? It gets to be a pain. So the larger your data set, the more likely you're going to want to make a histogram. So like I said, we're going to finish up the notes in the next video, so I'm going to go ahead and pause this, figure out what